Hey everyone, in this video we're going to talk about limits involving infinity. We're going to see what goes on when the inputs or outputs of our function approach infinity, what exactly we mean by that, and what kind of notation we use to describe such an event. So I'd like to get us started with this example where we're trying to find the limit as x approaches 0 of the function 1 over x squared. I want to approach this limit graphically and numerically. We'll start by doing it graphically. This function 1 over x squared is probably a function we have seen before that we should be somewhat familiar with. It's an example of one of those rational functions that is studied pretty heavily in pre-calculus. And if we remember what we learned about in pre-calculus, the function 1 over x squared looks something like this. Right, so we had what we called horizontal asymptotes as x went off to the far left or to the far right, and we had a vertical asymptote as x got closer and closer to 0. And really these limits involving infinities are often used to describe those types of behaviors of our functions, these asymptotic behaviors. So we see that this function increases without bound as its input gets closer and closer to 0 on either side. And when we are in a situation like that, we say that that limit equals infinity. So here, the limit as x approaches 0 of 1 over x squared is equal to infinity. But what we mean by that is that it increases without bound. That is, the output of this function increases without bound as the input gets closer and closer to 0. Remember, infinity is not really a number. It's more of a concept. Here, when we say this thing is equal to infinity, we're saying that it is increasing without bound. We can make it as big as we possibly want. So we verified that graphically just by looking at the output of our function as x gets closer and closer to 0. We can also verify that numerically. Let's go ahead and see what that looks like by setting up our table over here. So when we found our limits in our earlier examples numerically, we plugged in a sequence of x values in a case like this that is getting closer and closer to 0. And we looked at, well, what happens to the output of the function as we plug in those x values. We saw that often when the limit existed, that the outputs will get closer and closer to a single number. Well, here, if we want to show numerically that this limit is equal to infinity, infinity is not a number, so what we're going to be looking for is the pattern in the outputs just getting bigger and bigger and bigger. We can make it as big as we want. So we have to pick a sequence of x values first that gets closer and closer to 0. Technically, we need to do this from both sides. This is an even function though, so that means a negative input is the same as a positive input. So we're going to do it kind of quicker here, plug in both the negative and positive inputs at the same time. So maybe we could start with x pretty close to 0 on either side, maybe like x equals 1/10. Then we could get even closer to 0, maybe to 1/100th. We could get even closer to 0 by plugging in x equals 1/1000th or 0.001. And then I don't think we'll see our pattern probably at this point, but let's maybe just go one more further. If we plug in 1/10,000th into our function, let's see what happens to the output there. All right, so our function is 1 over x squared. It just takes the input, squares it, and takes the reciprocal of that, or it takes the reciprocal and then squares it. Either way, you'll get the same thing. So if we start with our first input of 1/10th, plug that into our function 1 over x squared, it'll evaluate to exactly 100. So now let's go ahead and fill out the rest of this table really quickly and see what kind of pattern we can notice with those outputs. All right, so I filled out the rest of our table, and we can see when we plug in the rest of our sequence of x values that are getting closer and closer to 0, technically on either side. Forgot my plus or minus there for a moment. Well, what happens with the outputs on each side is, well, the first one we got an output of 100, then we got an output of 10,000, then an output of 1,000,000. We can see it's getting bigger and bigger and bigger very quickly. The last one we plugged in, 1 over plus or minus 10,000, gave us an output of 100 million. So we can see that the output is getting bigger and bigger and bigger as the input gets closer and closer to 0. So what happens at x equals 0? Well, our function is undefined, but the limit is approaching infinity, or it is increasing without bounds. So again, the limit as x approaches 0 of 1 over x squared we say is equal to infinity. We also know that at x equals 0 we have a vertical asymptote for this function, and that's what these infinite limits, or these limits involving infinity, are really useful for. They give us a nice way to algebraically describe a vertical or horizontal asymptote, right? In this case, our limit involving infinity described a vertical asymptote, but with this function we could also describe a horizontal asymptote as well. So in this example, so far we've been able to describe the vertical asymptote this function has using the limit as x approaches 0 of 1 over x squared is equal to infinity. Another thing we know about this function is that it has a horizontal asymptote at y equals 0. We can use similar notation to describe this horizontal asymptote. What would we have to change in our current notation to describe this horizontal asymptote instead of this vertical asymptote? Well, if we think about it, what is a horizontal asymptote actually doing? And this is requiring some knowledge from pre-calculus that we may have forgotten. A horizontal asymptote is always describing the end behavior of our function. And what is the end behavior? Well, it's what happens to the output of our function as the inputs get really, really large in the positive or negative direction. Stating that in a way using our limit vocabulary, we're seeing what happens to the output of our function as the limit of x approaches positive infinity, or for the other side of the end behavior, what happens to the output of our function as the input x approaches negative infinity. And in this case, the output of our function as x approaches negative infinity or positive infinity, the output is getting closer and closer to 0. We can make it as close to 0 as we want just by making sure x goes far enough to the left or far enough to the right. So the way we would write that is in the following way. For the left end behavior of our function, we would say the limit as x approaches negative infinity of 1 over x squared is equal to 0. And for the right end behavior of this function, we would say the limit as x approaches positive infinity of 1 over x squared is equal to 0. I mentioned that these limits involving infinity are going to be describing our asymptotes. Whenever we have the limit as the input x approaches positive infinity or negative infinity, whenever those limits are equal to a finite constant number, that's going to be describing some horizontal asymptote to our function. So I want us to describe the asymptotes and end behavior of the function f of x that I have graphed up here. So let's go ahead and get started. Let's maybe just work our way from left to right. All right, so if we look at the far left of our function, try to describe maybe the end behavior as we move to the left or as x approaches negative infinity of our function. That's what the limit as x approaches negative infinity of f of x would be asking us. What is the output of our function doing as we head off to the left on our graph, or what is the end behavior on the left-hand side of our graph? And here on this function, we can see as we move farther and farther to the left, or as x approaches negative infinity, our function is approaching that horizontal asymptote at y equals 2, right? All these kind of hashed lines are indicating different types of asymptotes. That's what we pretty much use all the time to indicate our asymptotes. One thing to remember about these horizontal asymptotes in particular, horizontal asymptotes are only used to describe the end behavior of a function. They don't describe what kind of happens in the middle, and because of that, we are allowed to cross horizontal asymptotes like we did here, a little bit farther to the left of x equals negative 5. It's just describing really a horizontal asymptote, that is, what is going on far to the left or far to the right. I mentioned we're going to work from left to right, so we'll get to the right-hand side later on, but we can see right now the function does not approach this horizontal asymptote on the right-hand side. It's only approaching the horizontal asymptote on the left-hand side, so only the limit as x approaches negative infinity of f of x is going to be equal to 2. So now if we work our way from left to right, what would come next? Well, we see at x equals negative 5, we have a asymptote. We have a vertical asymptote. And let's see. So it doesn't matter which way we approach this x value of negative 5, if we come from the left or we come from the right, The output of our function is going down. It's decreasing without bound. So we would say the limit as x approaches -5 of f of x is -infinity. So be very aware in this limit notation where your infinity is at and what it's describing, right? In our first limit up here, the infinity is in the lower part of the limit. That's describing what is happening to x. X is approaching -infinity. In our second limit, infinity or -infinity is what our limit is equal to. And so that's describing the output of our function or the behavior of our function as x approaches -5 from both sides. So I think we've taken care of our first vertical asymptote at x equals -5. Let's move on to our next vertical asymptote, in this case at +5. So we might try to start describing the second vertical asymptote at +5 using a two-sided limit. But that would be inappropriate here because if we look at what happens at x equals 5 on both sides, it's not the same thing. As we approach x equals 5 from the left, our function is decreasing without bound, going down towards -infinity. But when we approach x equals +5 from the right-hand side, our function is instead increasing without bound, approaching +infinity. So sometimes we will have to use our one-sided limits and two of them to totally describe an asymptote. So in this case, we have to do that. The limit as x approaches 5 from the left of our function is -infinity, right? As we get closer to 5 from the left-hand side, we are going down. But the limit as x approaches +5 from the right-hand side or from above, well, that's going to go up towards +infinity. Our function is increasing without bound as x gets closer and closer to 5 from the right-hand side. So with these four limits, we've described all the asymptotes of our function, but we haven't finished describing the end behavior. We mentioned this one earlier, but what happens as x approaches +infinity, or what is the right-sided end behavior of our function? Let's see. Is the output of our function approaching a single number as x gets bigger and bigger or approaches +infinity? It does not look like it. It looks like, if anything, maybe our function has one of those slant or oblique asymptotes. It's just going up and up and up. So we would say the limit as x approaches infinity of our function is also equal to infinity. And remember, every time we say this thing is approaching infinity, we're really being lazy. What we really mean is the limit as the input of our function increases without bound, the output of our function is also increasing without bound. We can make the output of our function as big as we want, as long as we make the input of our function big enough. And so I think that's it. We have finished describing the asymptotes and end behavior for this given function using our 5 limits here.